Okay, let's start. Any questions on the assignment?
Sir,
Yes.
one question from the previous lecture, like, can you once more explain the status of all the high transistor?
Okay, so let's do it here right away. So sorry. Okay, so let's mark. This is I0. Let me call this one. I don't remember the marking, but let's call this M1, M2, M3, M4, M5. Okay, doesn't matter, right? Yeah. So let's all make it W by L. And this was W by 4L. Okay, so now we started off trying to figure out what is the minimum voltage at the drain of M2. Let's assume everything is biased in saturation to start off. Now you tell me what will be which node voltage will be what. And M2 is at, drain of M2 is at minimum possible level. You can start from the gate of M1. What is the gate of M1 voltage at?
2 VGS.
How can gate of M1 be 2 VGS? M1 is this one, right?
Threshold voltage plus the overdrive voltage.
Yeah, so threshold voltage plus overdrive, VGS. Okay, so which means this is also that. What is, if I am biased at the edge, what is the drain of M1 at? Okay. What is the gate of M2 at? V overdrive plus VGS. All these are for current of I0, right? Okay. What is the drain of M2 at? Plus threshold, right? So this, let me just rewrite. So this voltage is V overdrive plus VGS, which is effectively 2V overdrive plus threshold. So drain of M2 is at 2 overdrive, 2V overdrive, right? So again, this is at the edge, right? So now, which status of which transistor do you want to check?
Sir, mainly issue with the M4.
Mainly issue with M4. Okay.
Is it the saturation or is the?
Why you tell me? What is the drain of M4?
2V overdrive plus VTH.
Okay, so no, so the drain of M4 is VGS of M3, right? So threshold plus V overdrive, right?
The drain of M4 is?
Drain of M4 is the VGS of M3, isn't it?
So of M3, that is
V overdrive plus 1 threshold.
Okay.
Right. So now what is the status of M4? What is the difference between drain and gate?
The source of M4 is basically.
Why do you bother about source? It's the relationship between drain and gate, right? If the transistor is on, to figure out whether it is in saturation or linear, you just have to take into account the drain and voltage difference between drain and gate, right? So this is 1 V overdrive, and V overdrive is generally lesser than VTH, right? So we're fine. Threshold voltages are 300, 400 millivolt. Overdrive is 100 millivolt. So it's in, yeah. Okay, any questions regarding the assignment? How many of you have started? Okay, and any questions regarding the assignments? Yeah.
So that's the question that I was asking. I just saw you. So actually, initially I assumed that that simple current mirror.
Right.
That connected and there is a transistor. So initially I ignored the channel length modulation.
Yeah, that's the right thing to do.
Okay,
fine,
and I found out the voltage VGS.
Right.
And then I applied that voltage over here and find out the current.
Fine.
Okay. But by simply we can find out the voltage across this second transistor because the same current is flowing.
Right.
Okay. So there's two approaches. One is directly you can find out.
Right.
And another is ignoring the channel length modulation.
Yeah.
Applying the formula.
Right.
In both the cases, I am getting the different answer.
You will. So now the question is, what is the right approach, right?
Even sir, whenever I am considering this ignoring the channel length modulation, that time in the next second part you ask the minimum and the maximum value of current. So with respect to that, the transistor was going in the triode region.
Yeah, correct. So no. So I'm not sure whether that statement is correct or not.
Sir,
okay, fine. So I'll come back to this. You had a question?
Yes, sir. It's like the last lecture you discussed like for the P transistors you considered the effect of the channel modulation.
Right.
And you didn't consider the effect because you're saying that based on the P transistor itself we are setting the current.
Right.
So there itself we are considering it.
Right.
But in this case, like for wide swing current.
Right.
So how to say like for which transistors we have to consider that effect and for which?
Okay. Yeah. So generally, I mean. So if you have to consider the channel length modulation, then you have to figure out which transistor is setting the current. So here, I mean, typically the transistors where the gate can swing independently of the source sets the current, right? If the source is fixed and the gate is swinging, that essentially is determining the current. And which in this case is obviously this M1, M3, right? So, so that is one way of saying, but this is again a current mirror. So if you have to draw an equivalence between the current through M1 and M3, then you have to not only be aware of the fact that it's determined by the VGS, but there can be some difference due to VDS. So then you take into account channel length modulation of M3 and M4 and then see whether that second order of accuracy can be is applicable or not. So to the first order, let's say you are not bothered about whether the current is accurate within 1% or 2%, it's okay if it varies, then you neglect. But if you have been asked to exactly match, then you cannot. So that's the whole premise of it. So I will come, so I was expecting a question similar to this. So that's why I asked whether you have any questions, and you will only have questions if you attempt it. Without that, you don't have any questions. So it boils, I mean, the easier way to approach this, or I mean, I would argue that even a more accurate way maybe to approach this is this. So let's assume this is some voltage, right? I mean, being set by whatever. So VD. So normally when you do small signal analysis, you assume there is a quiescent, right? You assume there is a quiescent, and any deviation from quiescent, you use incremental, right? We are all on the same page. So here, when what is the effect of channel length modulation? The effect of channel length modulation is this: if VD1 goes up or down, the current through this stack will change a bit, not drastically, because this is anyways a very second order effect. It will change by a small amount or an incremental amount with respect to the quiescent. Fine. So the easy, I mean, so which essentially means that it is beneficial in our, I can remodel this problem and say that let me find out the quiescent for which I know that current in both the stacks are exactly equal, right? So under what condition do you think current in both the stacks will be exactly equal? And that I will call as a quiescent. So in this case, under what condition will that be? Saturation is a whole range of voltages by saturation.
VD1 is same as VGS.
Exactly, right? So when these two voltages are identical, right? At that condition, under those conditions, both my currents will be identical.
That is possible only when you neglect the second order effect.
No, even if you consider second order effects, because I am saying that my VGS and VDS are both identical. So there is no other solution. Correct. So you assume that under that condition, your I0 is identical in both branches, and that you set it to be your quiescent. And from that quiescent, you can figure out what is GM, what is GDS, and everything. Right? Now, once you know the GDS, so let's assume that voltage by putting in whatever effort you figured out to be some, I don't know, maybe 1 volt. Right? 1 volt or 1.5 volt or whatever. I don't know, don't remember the answers. So whatever it might be. So after that, once you figured out quiescent, once you have figured out the incremental parameters, you can forget about quiescent after that, right? You can simply say that if this drain voltage goes from 1 volt to 1.5 volt, how much current, excess current will flow? It will be whatever GDS times 0.5 volt, right? So it will be say I0 plus that, isn't it? And if it goes down, it will be I0 minus that. So that gives you the range, right? You don't have to go into third order equations, right? So you have to go into do that once to figure out what is I0. And if you choose, you can even neglect that. You can just say that under that condition, I mean, it's beneficial to do it once to figure out what is the actual solution, but you can even make that approximation and say that to figure out the quiescent, I will neglect GDS, I will neglect channel length modulation, and I'll assume that to be the quiescent, and then use my incremental. That is also fine, and that is the, I mean, I would argue the smarter way to do, because if you do the full-blown math, you will see that there will be slight difference in the exact I0 and or rather exact VGS and the VGS for which the currents are equal. But that's okay. You can neglect that. Okay. Yeah.
So, the problem that I was facing is that the MOSFET was going to the paired region.
Which MOSFET?
So can you draw that circuit?
This one, right?
No, that one. This for this question. So the current is given at 0.5 milliampere, and the VGS is 2 volt for the given parameter.
Okay.
Okay. Now I tried to find out the V out. I mean the VD1.
Okay.
Just applying the formula like I0 is half mu and C of WIN, VGS square into 1 plus lambda VDS.
Okay.
And lambda VDS is basically VD1.
Okay.
The VD1 that I'm getting is 0.
Oh, that's not possible.
Yeah, they're getting
0.
So they're getting 1 volt on the it cancels out. They're getting as 1 plus lambda VDS is equal to 1. So it cancels out and getting VDS is 0.
Then you have to take, I mean, did you consider channel length modulation both sides?
No, sir. In the left side.
Yeah, right. So currents will be equal when you consider channel length modulation on both sides, isn't it? So your question in the email was, when can I neglect the VGS with respect to then it boils down to what am I using that VGS information for? Right? If I am trying to get into this second order level of accuracy for current mirrors. And in one part of the mirror, I am neglecting VDS, but I am not neglecting that in the other part of the mirror, then you'll have errors.
Okay.
Right? So, but if you are making the assumption to start off that, okay, I mean, maybe there is slight change of, I'm only trying to figure out what is the range of VGS, then I can neglect. It's not a problem, right? Because it's like under cube root function. So it will be quite weak. So my answer was based on that. So it basically boils down to what you are trying to use that for, because you have to. So it boils down to error accumulation, right? So you are getting an error term by one method, but then you are multiplying it with a bigger term. So your error will increase.
So basically, I'm incorporating the error in the M2 part, like
right.
whenever I'm calculating the VGS.
Right.
And then in the next part, I am
correct. Yeah.
the accurate equation.
Yeah. Exactly.
That's basically creating the problem.
Yeah.
So another doubt with that question. Like,
so what I would say is that, okay, do it once, including channel length modulation for both M1 and M2, and also do it without. Neglect channel length modulation of M1 and M2, and to find out the VGS and see what's the difference. Right? So that's a good exercise to do. Yeah. What was the second question?
So next question, like what is connected above the VD1 node. Okay. We don't know. But
right.
Sir, if we use a resistor, or in the second case, we might use a voltage source that
fine.
we are varying.
Right.
So that the result will be different for both.
No, why?
Sir, if I use the resistor, suppose, and it's a very high value of resistance of RD.
Right.
In that case, if the current is high, in that case, the drop will be very high.
Fine. So
that might make the M1 to go in.
It can. But that's not what we are trying to figure out here. Here we are trying to figure out for what range of. We are not trying to figure out what sets the VD1.
Okay.
Something else might be setting the VD1, but assuming that VD1 is set, how much is the difference in current in the two branches? If you put a resistor, if you increase current, more drop, VD1 go to some value. But for that VD1, how much will the percent current be? So that is what we are trying to figure.
So for this case, one like when we get the VD, then first is like for minimum possible value to maximum, that is 5 volts. So first is I naught, and then other is difference. That value to 5 difference.
Correct.
And into RDS.
Correct. Yeah, essentially that. So the trick to all these things is to figure out the condition under which you have exact current matching, even taking into account second order effects, and then assume that to be the quiescent and move up and down based on it. So that's, I mean, we have small signal analysis for neglecting small types of errors, then why not use it in this case also?
And so when we move on to the next another problem,
We are
dealing with wide screen current.
Right.
So we are essentially like we have developed that model to mitigate these effects, like matching.
Correct.
So in that case, we can neglect the effect of channel points.
You can neglect if you are not bothered about it, but if, I mean, obviously in this case also, if you change this drain of M2, you will have some change, right? It's not, GDS is not 0 or RDS is not infinite. So the purpose even of the assignment, I mean, the simulation assignment is to show you that how much change you have been able to suppress. So it's not perfectly 0, but it will reduce. So you have to theoretically calculate and also have to simulate and see whether how much it has reduced. So basically the slope will change, right? The IDVD slope has to change in order to increase RDS, isn't it? So that's what essentially the purpose of this question, of this assignment is. Okay, fine. So let's move ahead. So till now we have been we essentially have been dealing with common source amplifier, and we have wrapped it around with multiple things. We have tried to bias with multiple configurations, but every time we ended up with this gain term of GM times RL, right? So differential amplifier was also essentially that. So let me just simply sketch a common source amplifier then. And let's assume these biases and all those things have been set up using negative feedback. So that's fine. But our gain in this case is minus GM times RL. And then we saw that that is, I mean, if you have RL here, there is only so much of gain you can get for a particular voltage supply. Then we said that we will not use RL. We will use a current source. We'll use a current source and then try to bias it using negative feedback. And if this is fine, then what will be the gain? GM-RDS, right? So AV in this case will be minus GM times RDS, or GM by GDS. Now the question boils down to how do I implement this current source, right? So in our case, in our case, we were using we are essentially constrained to you with the use of one current source, and we can use as many MOSFETs as you want. So that's not a problem. So we saw how to replace this current source in the tail transistor of my diff pair. Now we'll have to also, now what I'm trying to get at here is that how do I replace this current source at the drain transistor, at the drain side of this transistor, right? So now imagine that, or you don't even have to imagine that the question that it boils down to is the fact that if you use a transistor, the the looking in impedance to the current source has to be infinite. Now, if you use a transistor, obviously you would want to have the drain pointed to this node, to VD. You don't want the source to be pointed to this VD. Now we have, till now we have dealt with only one type of transistor, and that is NMOS. Now, if I have to replace this I0 with a transistor and an NMOS, what can I do? I can do this. And I say that this is maybe biased with some VB. But I mean, at this stage, you should be the first to scream and say that this will not work, right? Why will this not work? Yeah, right. So looking in impedance is 1 over GM, which is definitely nowhere close to what we want for a current source. We want of the order of RDS or even higher. So then one might argue, why not I flip it? Why not I mark it like this? I mean, transistor is physically there is no way to differentiate discern between a source and a drain. So I'll put the source on top. Right? This is still an NMOS. I put the source on top. So can I do that?
Yeah, but transistor must be in saturation.
Yeah, transistor has to be in saturation. But I mean, no. So this is still let's assume this is still is VB. Okay. So what I'm trying to get at here is that, is this even, I mean, I can, since I have a pen and a paper, I mean, I can put the symbols anywhere, but is it an electrically viable way of connecting? Because what is a transistor? I have a drain, source, and gate, right? So I have a drain, source, or rather, let me call 3 terminals.
So is this an NMOS or PMOS?
You tell me.
PMOS, right? PMOS.
Okay, I have reversed the, sorry, thank you. What I wanted to say was this. Yeah, right? Yeah.
The problem here is like the source should be connected to the minimum.
Right. So in case of a, so what I was trying to get at here is that you might want to this is essentially a symmetric device. So how do you discern a source from a gate? Is basically the one that is at higher potential is the drain, right? It's not as if you flip the device, the drain changes. So this still, even though you have connected it like this still will be the source, which means the accurate way of representing electrically will be this. So obviously I cannot use an NMOS, but fortunately we have a complementary device, which is a PMOS, where essentially the current and the voltage directions are opposite. So let me, just for the sake of continuity, let me spend a couple of minutes on this. So we have been using an NMOS transistor. So this is P minus substrate, this is N plus, and you have a gate. Okay, and the current flows from drain to source basically by marking one as the drain, other as the source. I have already internally I have assumed that the terminal marked as drain is at a higher voltage. So we saw that this will not work in order to make a current source at the top, which means that I want something which does exactly the opposite. And fortunately, we have that. And such a device is called an PMOS. And in case of PMOS, the body is N-type. And you essentially flip all the dopings around. This becomes P plus, this becomes P plus. This becomes gate. And you say that this is drain and this is source, then you automatically assume that the current is flowing from source to drain, because now this is a hole dominated current, right? So the current also flows here. So in the original case, the electrons flow and in this case, the holes flow. Okay, so the direction of the carrier flow is still from source to drain, but just that the carriers are opposite polarity, the current direction changes. So now in a CMOS technology, everything is generally made on a P-type bulk substrate, which essentially means that this entire stuff is P-type, but you have to then dig a well of N-type, right? You have to make the environment of a PMOS, bulk of the PMOS to be N-type, which means you essentially dope a part of the region with N-type, and on top of that you do is P-type implants. On top of this, you build oxide gate and so on and so forth, right? So once you, so this becomes your PMOS. So so from the electrical perspective, not from the making of the device perspective, from the electrical perspective, fundamentally nothing has changed. Just that I can say that in case of NMOS, my current equations were IDS, that is current flowing between drain and source. I'm writing for only the saturation part, mu1 Cox. So in case of a PMOS, it will simply reverse because the current is flowing from source to drain. You simply say that it's IST is equal to half mu P, where mu P stands for the mobility of the holes, Cox, VSG minus VT whole square, VTP whole square. Typically, VTP is negative, so we use modulus of that, 1 minus lambda VSD. Yeah, I missed WL both sides. Thank you. So W by 2L. Okay, fine. So which essentially means that if I am dealing with these type of equations, which are essentially identical, the way we figure out the incremental parameters are also identical. So your GM here, I mean, you can use your favorite expression, whichever it might be, is 2 mu Cox W by L ISD. Here will be GM will be under root 2 mu Cox W by L. So it is IDS ISD. Okay. Similarly, in the incremental model, in the incremental picture, our incremental picture is this for an NMOS. If this is VG, the current, incremental current is GM times VGS, right? So this is VS, VD. But since everything has flipped, one might say that I will simply keep the current directions, the direction of the arrow same, then this will be GM times minus VGS, right? But we tend to do the opposite. We say that, okay, so let me mark it like this. Let's say this is drain, this is source, then this becomes GM times minus VGS. But we don't like to see minus and all those things because it messes with the head. So what we essentially say is that we'll just flip the direction. We'll flip the direction and make it GM times VSG. But again, we are not particularly comfortable with current going from bottom to top. Like gravity, like from top to bottom is the force that we are more accustomed with. So we say that we'll flip everything and keep this current direction same. And this remains GM times VSG, right? So this is what this is typically the model most people tend to use, and which I also find to be, more intuitive, because ultimately, in case of a PMOS, so let me also draw the symbols. So there are a couple of symbols which are used to mark a PMOS, the one that I had already used mistakenly earlier. So with the direction of the arrow is pointing towards inside towards the gate, just to show that the current direction is in the direction shown. But also there is one more symbol, that is this uses bubble. Typically this bubble symbol is used when you are using PMOSs in digital circuits, but it doesn't really matter. You can use either. So this is gate source drain gate source. So in case of the one thing that you have to keep in mind is the fact that in case of when you want to turn a transistor, NMOS transistor on, you have to ensure that the gate is at a higher voltage than source in case of an NMOS, but in case of a PMOS, you have to ensure is that gate is at a lower voltage than source, right? So it's this. So it's VSG in case of a PMOS that matters, and it's a VGS in case of NMOS that matters, right? So fundamentally nothing is different, but it's basically just getting used to. So what I would also say is that I haven't put it in the assignment, but all the current meters that you have in the assignment, do it for PMOS also, right? Nothing will change, but the fact that you will get used to flipping the notations, flipping the symbols. So, I mean, the more you get accustomed to it, the less chances that you will make silly mistakes when there is a time crunch also, right? So it's better to practice that. Okay, fine. So now I assume there is no questions here, right? Okay.
In small signal, PMOS and MOS are same. You can't.
Yeah, it's ultimately a voltage control current source, right? So controlling terminals are also the same, and just that the directions are different. And we have also rotated around in such a way that it doesn't really matter. So another quick way of, I mean, if somebody is looking at PMOS for the first time, but you are already comfortable with doing an NMOS design, right? There are two ways to approach that. You can then say that, okay, I will do the same design again for PMOS from the scratch. That is one way of thinking. The other way of thinking is this. So let's assume that you have, let's say, again, let's say assume a common source amplifier biased with constant voltage, right? So let's assume this is R1, R2. This is RL. You have figured out how to bias, right? This particular configuration, but you want to do the same thing for in case of a PMOS. So as I said, you can again write the equation, figure out what the limits are, what the values of R1, R2, RL are. But the other thing that you can also do is to say that, hey, I already know this. So what I will do, I'll just simply replace this NMOS with a PMOS. So I'll simply replace this NMOS with a PMOS. And I will not change the source drain terminal initially. So let me keep the source drain terminal to be the same. Okay. And I will change nothing. I will keep this RL. Keep this one as R1. Keep this one as R2. But I know that my current flows from source to drain, right? From towards source to drain, which means my higher supply voltage has to be this terminal. So this has to be VDD. This has to be ground, right? So, so once, I mean, then again, the problem is we are seeing current flowing from top to bottom, bottom to top, which is kind of unwieldy. So what I'll do, I'll take this and simply flip it around. So what I will do, I'll just flip it around, top, it becomes VDD. This becomes RL. This becomes R2. And this becomes R1. And this was, if this was my V0, so this becomes my V0. Okay. So assuming under the condition that these terms, mu Cox W by L, mu P Cox and mu N Cox W by L are identical in both cases, then you will see exactly same quiescent conditions. and even the same incremental conditions, bias conditions in the PMOS and the NMOS cases. Okay. The other thing is, I mean, this is also, I'm sure you know, generally the hole mobility is smaller than the electron mobility. So mu p is generally of the order of 2 or 3 with respect to with respect to mu n, which essentially means that if you have to pass same current through a PMOS which is exactly identical to an NMOS, then you will have to increase the W by L by that factor of mu p by mu n or mu n by mu p, right? So that the current remains the same. Also, similar things goes for small signal parameters also, because wherever you find GM, you see W by L and nu coming in. So if you want to keep the GM same, you have to also scale W by L in a proportionate manner if you want to keep the incremental parameters identical. Okay. So I assume you know all these things, right? So this is just for continuity before we move ahead. Any questions?
So for incremental model, both the PMOS and NMOS.
Yeah.
So it seems to be same exactly, that current injection is different.
Right.
So we can drain both the transistors PMOS and NMOS at the top. Drain as at top to the source at the bottom.
Yeah, you can do that, but the current then flows into, I mean, there is nothing wrong in doing that. Just that then you'll have to make your current direction this to be inverted. If you are comfortable with that, go ahead, no issues. Just that, yeah.
The drain will be a top side and the source will be bottom side. So both the model will be exactly.
It will be exactly same as far as this model is concerned. But now the issue is, you'll see the issue. I mean, mathematically there is no issue, but there is an issue of convenience. So you will see why I am saying that. So essentially now I hope you are convinced that we have, instead of a current source, what I will do is I will use a PMOS. This is VDD, this is the source, this is the drain, right? So now, how do I bias the, let's assume this is biased. How do I bias this this is M1, this is M3, let's say. How do I bias this M3? VSG of M3 for a current of I0, because I'm replacing it to provide a current of I0, right? So how do I get this I0 current? Diode connected what?
G should be tied to drain.
G should be tied to drain. So if I connect G to D, will this work? Who is setting the current through this M3 transistor now? It will be in saturation, no issues.
Impedance will be very small.
Correct, right? So, okay, so I'll get, let's get to the impedance first, then we'll get to who is setting the current, right? So what is the impedance looking in here? So I'll just replace it with, let me replace the entire thing with its small signal equivalent, right? So incrementally, the M1 is this. When I'm trying to figure out the impedance, I basically short the gate. And this is GDS of M1. And in the top, what will I do? So I'll have to replace the incremental model of M3, right? What is the incremental model of M3? Or rather, what is the incremental equivalent of M3?
Top it is source. Right?
Top it is source. So, okay. And then right, and this is gate. This gets shorted, right? And what is the, this is GMP. Now I have to differentiate, right? This is GMN. This is GMP times what? VSG, and VS is PS minus VG. And drain and gate are essentially shorted. But does that answer your question?
Yes.
Right? So if I had flipped it just to make this model equivalent, right? If I had kept the drain on top, then the connection here would have been very unwieldy, right? The drain goes on top, you have to connect it like this. So it basically boils down to we are comfortable of seeing going from top to bottom, right? I mean, there is nothing fundamental to this, right? Just that we don't want any more complications than we already have. Okay. Source will be grounded. So what will be the incremental impedance looking in? 1 over GMP, right? 1 over GMP. Direct connected transistor 1 over GMP. Okay, fine. So this clearly will not work because it's I mean, the output impedance of M3, direct connected M3 is very low. But again, I mean, let me not get into the incremental impedance, but let me ask you, who is setting the current in this stack? There will be some current that will flow, but will it be equal to I0 or will it be equal to what? The way I have sketched, exactly take it at face value. This is what I have sketched. There is nothing, no negative feedback here and there. This is what it is. Then who will set the current?
So current is set by M1.
Current is set by M1 because you have this, if this is VB, you have this VGS, which is constant, right? So this whatever current this M1 will give because of this VGS of VB, that will be the current. That will set this I0. And this will might not necessarily be the I0 you want. Whatever it is, and that will in turn set this voltage here. Because this I0, this M3 is drawing out current of I0. So the VSG of M3 will be equivalent to the VSG required to draw a current out of I0, and that will set gate. So this will clearly not work. So what else can work? I still want a current source of equivalent to I0 here. So what should I do? Assume that you have a master current source somewhere, or you don't even have to assume. I mean,
copy that
required voltage at that point.
Right. So essentially, I mean, I have to leave the drain as is. If I connect the drain with the feedback, then I am losing output impedance. So I cannot really do anything like this. But I want current of I0, and the current I need it to set. I want the current to be set by M3, not M1, right? So which essentially means that I have to apply some battery here. Right, I have to apply some battery which is holding some VSG value, which corresponds to the current of M1, current of I0. Okay, so how do I hold a battery? How do I mean, I can simply say that, I mean, think in terms of your, when you are doing M1 biasing. So when I say I'm holding a battery, what I'm saying that in case of M1, just like I have a VB, I probably will have some battery here, which is holding that value, that magic value. So now, if you want to do that, what is the problem that we faced for an NMOS biasing? Constant voltage biasing. Two independent sources fighting each other. Then you will have your small signal parameters are not particularly constant with respect to ambient changes and so on and so forth. So you want constant current biasing. So for constant current biasing, we do a whole lot of things, right? We spend, like, I think, more than enough time. So one way of setting, I mean, we can do all of those, or else we can also do this, right? We can simply say that, how do I push in a current into one branch when let's assume I have a current source somewhere else? I can simply mirror that current, copy that current, right? So just like in case of a NMOS, I can copy that current. I can simply copy that current, and if I again neglect channel length modulation, okay, so this has to be there. If I neglect channel length modulation between M3 and M3A, then the current will be exactly equal. But if I don't, then there will be some difference, but that's okay. Okay.
So GB also can be replaced.
Yeah. So let's, okay. So there is a problem with this architecture if I leave it as is. Because now you are seeing that, I mean, the transistor in the bottom M1 is biased with a fixed VGS, which means it's probably asking for some current I1, and that one on the top is trying to push some current I0. So this clearly will be a problem. So this is a problem if you leave it as is, but this is not a problem if you think that maybe there is an overall negative feedback loop, which I haven't shown here, which is essentially making this VGS variable. VGS of M1 variable. Maybe this VB is a variable voltage source. Maybe there is some feedback which is connected. Some feedback way of connecting, right? So we have seen whole bunch of feedback way of connecting this, and this is what there is always an assumption, right? There will be some negative feedback which is setting. The other way to think about is that what we were essentially trying to achieve, we are trying to achieve a amplifier whose amplification factor should be high when we analyze it in an open loop, right? Okay, that statement is not exactly accurate. What I'm trying to get at here is that if you break the loop, you should see a lot of gain, right? So which essentially means that's why we analyze the amplifier in open loop. But the assumption in the back of the mind is that I'll put it in a closed loop, because an amplifier cannot work in an open loop. It will saturate, right? Because of difference in current and all, it will either go to VDD or ground. So you never use an op-amp in open loop, for example. So if I assume that at the back of the mind that there is negative feedback which is keeping the bias constant, I can say that I will use this in an open loop. I will analyze this in an open loop fashion, which means that maybe I have applied my input here, and I will try to figure out what is the gain between V0 and Vi. So what will be the gain between V0 and Vi in this case? Now, obviously, if you neglect GDS of M1 and M3, what will be the gain? Incremental gain. So again, I'll replace this with my incremental model. So I have Vi here. So this will be GMN Vi. I neglected GDS, so nothing there. Then on top, I have this. What is my gate at? Incrementally, what is my gate at? Not perfectly ground, right? Because what is the impedance looking here? No, it's diode connected there, right? If you excite, it's 1 over GM, right? If I look through this, so essentially 1 over GM to ground, isn't it? If I neglect GDS and all, so what will be the incremental model of this? So what is the incremental model of a diode connected, an NMOS diode connected transistor, for example? Correct. And if this is current source here, which is open, then what do I get? 1 over GM to what? To ground, right? GDS I neglecting, right? So I'm neglecting. So this is essentially GMVGS, or rather GMVG, and this is VG. So I am applying a voltage of VG and I'm pulling out current of GM times VG. So this is equivalent to 1 over GM to ground, isn't it? So this is essentially 1 over GM to ground. But for our case, it doesn't really matter then, because this voltage will also be ground, because I'm not pulling any current through that 1 over GM resistor, which means no incremental current. Yes, which means this is V0, which means what is this? No. What is this GMP times VGS? Right. So this is 0 minus 0. Right. So essentially this goes off, and I have a current of GM times VI flowing into an open circuit. It means I am getting a gain of infinite, and that shouldn't surprise us if we neglect GDS, which means we are essentially saying that there is no incremental load at the output. So I mean, I am pushing some current, I'll get a infinite gain, but that is not a very good approximation, because I mean, you can neglect some small number with respect to a large number, but when you say it's infinite, when it's not, then you are making an infinite error. So you shouldn't do that. So you then you say that, okay, I recognize the fact that there is a GDS, and that GDS is, there are two GDSs in fact. So there will be a GDS N and there will be a GDS P. So what will be the gain? Yeah, so the short circuit, I mean, you can directly see in this case, but the more methodical way of going about doing is figuring out what will be the short circuit current, figuring out what is the output impedance, and then multiplying the two, right? So my short circuit current in this case, ISC, will be GMN times VI minus of that, because I mean, depends upon how you define ISC, right? So if I define ISC in this direction, and this is grounded, so this becomes minus GMN times VI, and what will be R out? It's basically you incrementally short VI, which means there is no incremental current, and the GMN times VI goes to 0, and the transistor on top was anywhere 0. I mean, the current contribution of the transistor from simply because I am not exciting the gate and gate to source voltage. But there is a GDSP, which means that, what is my R out?
1 by GDS.
Two conductances in parallel, they simply add up. GDSN plus GDSP, which means my gain now becomes minus GMN by GDSN plus GDSP. Okay, so my in terms of the incremental, in terms of my incremental Norton equivalent, or I mean the incremental Thevenin or Norton equivalent model of this entire configuration, nothing has changed, just that this if I assume that this is the stuff in the box, and we are essentially trying to figure out what is it from looking in from the outside. So this is GMN times VI, and this is 1 over GDSN plus GDSP, right? So when you didn't have the PMOS, the current source was, the control current source was still GMN times VI, but just that you had 1 over GDSN or RDSN instead of a resistor, in place of the resistor, but the value of the resistor essentially has changed in this case. Okay. Okay. Any questions?
Sir,
yes.
The last circuit, why you have replaced it with that battery? So there is no difference.
Here in this circuit, right? Okay. So what you are essentially asking is that it seems like there is one I0 from top, one I1 from bottom. It's a problem. It's a problem, but you have to recognize the fact that we will not be using this as is. It will be a part of a broader negative feedback circuit, which will ensure that I0 equal to I1. While I am essentially assuming that maybe there is a negative feedback, which is going and controlling this battery.
Just for analysis purpose?
Yes. So you use, I mean, we are more comfortable in analyzing circuits in open loop, right? Analyzing circuits in feedback is slightly more complicated. So we try to break the loop and then find out its open loop transfer function always, right? So when you, in that A beta model of feedback, you try to figure out what is A separately. So this is essentially the purpose of figuring out A, right? So that's always the case.
When we close the loop, like when we provide the biasing for this M1, will there be any change in this gain expression?
I'll come to you. Yeah.
So when ISC will be doing the account of
While figuring out ISC, I didn't get the question.
you have to take the GDSP and
Okay. So his question is, while figuring out ISC, should I take into account GDSP and GDSN? What do you think? Should I, or I can leave it as is?
They will take it into account. It will be they are providing a short circuit.
Right. So the both sides of this GDS and GDSP are shorted then, right? Because ISC is going into a short circuit. The other side of GDSP and GDSN are also shorted, incrementally shorted. So they are out of the picture, right? Yeah. Your question was, what was the question?
So, sir, in the open loop case, we are trying to find where we have identified the gain.
Right.
Okay. Now, for biasing purpose, we're closing the loop, providing the feedback.
Right.
Will there be any change in the gain?
No. So will there be change in the gain? Which gain?
Expression of gain, that is V out by VI.
Okay, there won't be, right? Because what is the gain? I mean, regardless of however you connect this circuit, the relationship between drain and gate remains the same, isn't it?
Sir, I'm thinking that way, like when we have a closed loop system,
right?
The closed loop gain is basically A by 1 plus.
Yeah, but then where is the input applied? So, okay, so let me go back to this model again. So when we say that, when we are trying to figure out the open loop gain of A, which two terminals am I looking at? Forget about breaking. Which two terminals am I looking at? VE and V0. So the relationship between VE and V0 is what? So V0 by VE is what? It's A, regardless of whether it's in the loop or not. So now what you are essentially saying is that in one case, the open loop, I'm applying the VI here, I'm breaking it and applying the VI here. In the closed loop, I have now changed my VI application, right? I've changed it, put it here. They are not identical cases. So if you have to figure out the gain, you have to keep the input application of the test input and your observation point the same. You cannot really move them around and say that it has changed. Right? That essentially is the reason. I mean, one way to argue that why do we have virtual ground is essentially that. It's because this is always A, and if V0 has finite excursion, and if A is very high, this has to move low in order to keep that gain A. Right? The A is very high, so which means that the input of this amplifier cannot move, because you have gain of A, even if you have put it in feedback. If I put it in feedback and the gain goes off, then what's the purpose of the designing of the amplifier? The whole purpose we are designing a high gain amplifier is because minimize the error, put in negative feedback and it will minimize the error. It can minimize the error only if it has high gain. If you put in negative feedback, gain goes off, then there's a problem. And that when you will design a circuit, you will see that that typically happens because the bias changes. You probably initially, when you put things in negative feedback, I'm not saying it happens all the time, but the fact that we sometimes miss maybe a bias here, maybe a bias there, and we put in when we connect something through this like this, you will see that often due to negligence on our part, maybe some bias gets. We assumed while designing this open loop amplifier that there is certain bias. Because after you put it in negative feedback, sometimes you will see that the bias goes for a toss. In that case, you will see that, wow, whatever is structured in class is wrong. But that's not the case. It's basically because the bias goes off. And if bias goes off, your small signal parameters goes off and you have a problem, right?
Sir,
yes.
Sir, in comparison to that block diagram, this VI is equivalent to V error and V out is equivalent to the output of
correct.
V, right?
Yes.
And if we see that block diagram, the VI, this VI is grounded.
This VI is not grounded. I mean, we applied it.
Some DC.
No, you can have, okay. With respect to that, yes. With respect to that, yes. Some DC voltage we will. Okay, any questions? But this is thanks for bringing it up, but this is a very common mistake that I have seen students do. I mean, they think that I have put in negative feedback, so the gain has gone down. Yes, gain has gone down, but not between the nodes that you were looking at. From your actual input to your final output, yes, the gain has stabilized, it has gone down, it has stabilized, fine. But your actual input is no longer the input of the amplifier. Okay, fine. So, so we have another 10-15 minutes. So let me take this opportunity to show you something here. I mean, so we did this, right? So let me approach it from the perspective of small signal, then I will come back to the full blown. This is VGN, this is VGP. I am taking my output from here, V0. Okay, so if we apply the incremental input at VGN, we saw what we get. But from the small signal perspective, is there any difference between applying the gain input at VGN and applying the input at VGP? Is there any difference purely from the small signal perspective? Let's assume GMs are same. I mean, we are biased in such a way that the GMs are identical. GMP and GMN are identical, let's assume.
Both are branch in the top and it's like a parallel connection in the small signal sense.
Kind of, if you take the output at V0, but I mean, will the gain change? If the small signal parameters are identical, will the gain change? Nothing will change, right? So I might as well choose to apply my input at VI. Apply VI at VGP, correct? Then what do you want to do with VGN? Bias with the current source. Basically, flip whatever we had done here, right? So apply the VI at M3 and bias M1 with the current source, right? But incrementally, can I also apply VI at VGN? I can, right? I can apply VI at VGN. So if I am able to do this, what will be my gain? What will be my gain? Somebody from this side, yeah, Arya? The way I have sketched it, this is the full incremental model. So what will be the gain? What will be ISC? Yeah, if you assume GMN and GMP to be identical, you'll have twice, right? So this current will still be, the current that will be coming here is GMN times VI, and current that I will get through this will be what? Which direction? So this is GMP times VSG, that is 0 minus VI, right? So this current will go up. I mean, sometimes you have to deal with currents going up. So this becomes GMP times VI. So what is ISC in this case? Minus GMP plus GMN times VI. What will be R out? It's same, right? Nothing changed because I essentially will be grounding PI. GDS P plus GDS N. So what will be my gain? Open loop gain is basically minus of GMP plus GMN by GDSP plus GDSN. And if you assume these are identical, GMP is equal to GMN and GDSP equal to GDSN. So essentially you get double the gain with respect to the other configuration, right? In the other configuration, you only had short circuit current was only GMN times, but the output resistance was same. But in this case, the short circuit current is GMN plus GMP times, but your output resistance is, your output resistance remains the same, but your short circuit current has increased. Right. So you obviously would want higher gain. You are striving for higher gain. This seems to be a better option, right? We can do that. So now, if you are convinced, we can do that. By the way, are you convinced that this is fine? Better than the earlier option? So if this is better than the earlier option, then you have to figure out how do I bias, right? This is the small signal equivalent. So how do I bias? So let me replace. I can do it here itself, but it will become clumsy. Let me take it down. So we were applying VI directly at the gates, right? At the gates of M1 and M3 in the incremental sense. But if I am not concerned about incremental input, I am only concerned about bias. So that I can remove VI. And then incrementally, that is 0 then, which essentially means that the VGS of M1 and M3 are constant, right? So which means I have bias here and I have a bias here, right? This is the bias picture. But now we end up with the same old problem. How do I apply VI, right? Because I have a VI somewhere here. Maybe it has a resistance and also here. Let me neglect resistance because we have not been considering that. But how do I apply VI to M3 and M1? That becomes a problem, right? So now, what do you think? What should I do? I can use a capacitor. Also, I'll have to decouple this, right? Because if I keep this VGS, if I use these batteries, then my VGS will never change, right? So I have to decouple. I can use a capacitor and all those things. But yes, you can in fact do that, and that is done many times. But let me show you something that is actually quite interesting, and that is the fact that initially, let's say I want to bias anything. Let's say I can think of it as, let's say M3 is providing the current for M1, and also I can assume that M1 is providing the current for M3, right? For the purpose of my analysis or for the intuition, I can assume that some current, maybe I naught is coming from, or let me call it I3, because that is what is setting. So, and if this has to work properly, I have to use negative feedback, right? So I can use this. This is M1, and in case of M3, I can essentially say that this is probably I1, let's say. M3. Okay. So now, if you think back to how we can, one of the architectures that we did was applying VI directly to a diode connected transistor was not a feasible option. So what did we do? We used a resistance here, and then maybe this had an RS and all of that. That's fine. So maybe a large resistance, let me call it R infinity. We applied it here and got it done. Similarly, we can do this here also, right? Okay. So now if both M1 and M3 are sized appropriately, right? So then it's quite likely that, and also we had a capacitor here, isn't it? So in the incremental picture, in the bias picture, this capacitor goes, Vi goes, and we are left with two pseudo diode connected transistors. I say pseudo because you have this R infinity in between. So what will this look like then? I mean, now I want to do the same thing in our case here. So that essentially will look like this. Okay. And then I say that I apply my input directly here. Fine. What is this purpose of this R infinity? No, I mean, the major purpose of R infinity is to ensure that my bias is set. Correct? So let me resketch this. So let me. Basically, these two are parallel, so this becomes R infinity by 2. Okay, and I have an input here, which is connected like this. Fine. Now, if I think of this stuff, then this purpose of R infinity is essentially to give negative feedback for biasing. But that is not a part of the code amplifier. So what is my code amplifier? So I can think of this R infinity. I mean, it's basically right. So what is my code amplifier? Code amplifier is an inverter, right? So you can what I'm trying to point out here is that you can even use an inverter for an amplifier in place of a so-called common source amplifier with a resistor on top. But the good thing about this is the fact that in case of an inverter, you are getting the transconductance of both N and the PMOS to help you increase the gain, maybe by a factor of 2, right? And you can rely on a negative feedback from somewhere else to stabilize your circuit, stabilize the biases. Okay. Any questions?
So this amplifier is very high gain.
Yeah, I mean, whatever is high, double that of a common source, if you think of that way.
Do we use that amplifier in any practical application?
Yeah. I mean, nowadays it's a very commonplace simply because, see, one problem is you have, so VDD is very less now in today's technology, right? 1 volt, 1.1 volt, sub 1 volt. So which means that you cannot use a resistors out of question, which means you have to use a current source, which means you anyway need to put a PMOS on top. Now, the question is, if you use a PMOS on top, why will I let its transconductance go away? I mean, it's coming for free, right? If I just connect it, I'm just getting a gain of 2. Why would I let it go away? Right? So in most practical cases, in today's analog world, we use inverters as amplifiers.
Because sir, I'm asking this question because if we see that transfer characteristics of a inverter,
right.
There's very small region in which we
okay. So that good that you asked. So that is an usual question I get. So this is V0 over Vi. So you are saying essentially this is my part, right? Where I am getting this high slope, right? So let's assume that I have exactly this configuration. I have gotten this slope, right? So let's now assume I have replaced this M3 with, I have not used this inverter, but the usual active load. By the way, this is called active load because you have a transistor on top. So I have used this current source on top. Okay, you're comfortable with the current source on top. So I have used this current source on top. So what will be this? What will be these transfer characteristics then? What I'm saying is, let's assume you have an ideal current source. And you have bias state and all, right? So what will be the relationship between these two nodes, this node and this node? how will it look like if I superimpose it on top of this? I'm more interested in that slopey state. I mean, slopey transition period, transition part of the plot. Will the slope of the transition part change? So what is the gain here? If you assume GDS equal GDSN equal to GDSP and GMN equal to GMP, what will, in case of an inverter, what is this slope? Assume it to be a straight line for convenience. What is this slope?
So the GMP plus GMN divided by.
Yeah, and if they are equal, it becomes GM by GDS.
GM by GDS.
Right? Which is the gain? That is the gain, right? So what is the gain of this configuration?
It will be like
GM by GDS. So what is the slope? Doesn't change.
But sir,
hold on. So slope doesn't change, right? So essentially this part will be superimposition, right? So now when it superimposes, then what happens to the case when output is very low, right? When I'm operating here.
Sir, here there will be no issue with the as we have used the current source.
Right.
Assuming the ideal current source.
Yeah. Okay. So you'll have to then cannot assume that, right? Because the current source will now it's not now a MOSFET. You have to assume it's a MOSFET, and I'm neglecting the GDS of the MOSFET, right? So let's assume this is a MOSFET biased with a constant voltage, right? You're neglecting the GDS of the MOSFET, then what happens?
So it will offer a resistance of GDS.
No, that is when it's in saturation. Whether will it be in saturation when you are going far away from this?
No, it will tend to go.
Right, it will tend to go to triode and it will become cut off. Sorry, I mean the NMOS will become cut off, right? If you are at very low input, right? So essentially you will have a similar curve. So you are always operating in this narrow range, regardless of whether you are using an inverter. I mean, think of it an ideal op-amp. What is an ideal op-amp characteristics? What is the transfer characteristics of an ideal op-amp? With finite limits, supply voltage. So it will go like this and fall like this, right? That's why you get infinite gain. Because you have infinite gain, you have no room to move. Right?
Under the matching condition, like when you are matching the PMOS and NMOS are matched, in that case, the gain for this contraption is same as this contraption.
Correct.
Right? Here we are applying the signal in the both PMOS and NMOS, but here we are applying only in the NMOS.
Correct.
But they are matched, so the gain is same.
Yeah, and I have neglected the GDS of the PMOS in the second case, in this case, right? If you neglect, if you consider the GDS of PMOS, then the gain is half, right? Half of the inverter. So it will become like this.
Nice.
Right?
And also, so from CMOS inverter point of view, we can say at that slope, both the MOSFETs are in saturation. And we can only use MOSFET as a amplifier when they are in saturation.
Correct. But I mean, you have to make sure that they are in saturation, and this R infinity by 2, what we're seeing here is the one that is holding it to saturation. Okay, you cannot simply have an inverter plug in a signal and hope that the thing is in saturation. In order to keep it in saturation, you'll have to have a negative feedback. That's always true, regardless of in a common source amplifier or an inverter. Okay, we are out of time, so let's stop here.